So on Tuesday, we talked about the ideal gas law. PV equals, or no, excuse me, that was on Monday. We talked about the ideal gas law, which is PV equals nRT. Now, what we're going to talk about is there are other variables that we can determine by deriving slightly different equations from the ideal gas law. So let's look at that. Well, the very first one is if we take PV equals nRT and we rearrange that equation, P over RT is equal to N over V. Since N has the unit of moles and V has the unit of liters, that means that P over RT is equal to the molarity. So we can talk about the concentration of the gas in solution. So that is one variation of the ideal gas law that we can use. Is again, we can calculate this molar volume by simply rearranging the equation and solving for a pair of variables rather than a single variable. The second equation requires us to do a little bit more. We start with PV equals nRT, but what does N equal? Well, N is moles. And if we're talking about dealing with some stoichiometry, we obtain those moles by taking the mass of the material and dividing it by its molar mass. And that will equal moles. So we can take and get PV equals mass over molar mass times RT. Now what we have is we have an equation that will allow us to calculate the molar mass of a gas. Say we don't know the identity of the gas. Well, if we calculate the molar mass of the gas, we have an opportunity to figure out the identity of the gas. So now we have another variable that we can calculate. We could also calculate the mass of the gas. So that's three new variables that we can calculate from the ideal gas law. Now there is a fourth that we can calculate as well. Well, here I actually get into the molar mass on the right-hand side, which is great for determining the identity of the gas. But on the left-hand side, I give you another one we can calculate by doing that substitution. So PV equals mass over molar mass times RT. If we rearrange that equation so that the pressure times the molar mass over RT is equal to mass over volume, well, what is mass over volume? It's the density. So you can determine the density of the gas by multiplying the pressure times the molar mass over RT. All of this coming from the ideal gas law and a little bit of stoichiometry. So basically, by being able to take the ideal gas law as our starting quantity, not only are we able to determine P, Z, N, and T, like we have been doing, but now we're able to determine the molarity of the gas. We're able to determine the molar mass of the gas. We're able to determine the mass of the gas. And we're able to determine the density of the gas. Lots and lots of variables that we have discussed since early in the semester. We discussed density. We just now have another equation for calculating density from a gas. or of a gas. So just like the last few days, the main thing I'm going to do is work practice problems, because I feel like that is the most useful of our time. So calculate the density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeters of mercury. Okay, so the density is mass over volume. And that is what we want to calculate. We are told that we are working with nitrogen gas, which is N2. So the molar mass of the gas is going to be equal to 28.02 grams per mole. We are told that the temperature of the gas is 125 degrees Celsius, and we are told that the pressure of the gas is 755 millimeters of mercury. Now, the first thing we need to do, because we are going to be required to use R, which is 0.0821 atmosphere liters per mole Kelvin. The first thing we're going to need to do is make all of our units match. So we need to make this temperature unit match by adding 273.15. So that's 398.15 Kelvin. And we need to make our pressure unit match by dividing by 760. So that is 0.993 atmospheres. Again, the base gas law that I am using is PV equals mass over molar mass times RT. Okay, so we can take and get PV over RT is equal to the mass over the molar mass by dividing both sides through by RT. We then multiply both sides through by the molar mass, and you get PV times the molar mass over RT is equal to the mass. Dividing both sides through by volume, we then get P times the molar mass over RT is equal to the mass divided by the volume. Now the question is, and that is equal to the density. So the question is, do we have the pressure? Yes. Do we have the molar mass of the gas? Yes. Do we have R? Yes. Do we have temperature? Yes. So we can do this calculation. So the pressure is 0.993 atmospheres times the molar mass of the gas, which was 28.02 grams per mole, divided by the R, which is 0.0821 atmosphere liters per mole Kelvin, times the temperature in Kelvin of 398.15 Kelvin. And that will give us the density of the gas. And so the density of the gas comes out to be equal to 0.851 grams per liter. Which is actually very dense for a gas. Yes. You're going to have the conversions, yes. You have to know what STP stands for. Yes. Other questions? Let's look at another example. A sample of gas has a mass of 0.311 grams. Its volume is 0.225 liters at a temperature of 55 degrees Celsius and a pressure of 886 millimeters mercury. Find its molar mass. When I see that I want to find, by the way, when I saw that I wanted to find density, when I see that I want to find molar mass, that tells me that the equation I'm going to use is PV equals mass over molar mass times RT. Rearranging this equation, I'm going to divide both sides through by RT. And I get PV over RT is equal to the mass divided by the molar mass. Dividing each side through by mass, I get PV over mass times RT is equal to the 1 over the molar mass. I use my inverse key here. And when you use your inverse key, basically what you're doing is you take your mass times RT over PV, and that will equal the molar mass. So let's look at all of these pieces. I have the mass of the gas, that is 0.311 grams. I have R, which is 0.0821 atmosphere liters per mole Kelvin. I have the temperature of the gas, which is 55 degrees Celsius, and knowing that it has to be in Kelvin, that means it's 328.15 Kelvin. I have the pressure of the gas at 886 millimeters of mercury. Which I know needs to be in atmospheres. So I divide by 760, and that gives me 1.166 atmospheres. And the volume of the gas, which I missed, was 0.225 liters. So I have all of the information in order to calculate the molar mass. So the mass of 0.311 grams times R, which is 0.0821 atmosphere liters per mole Kelvin, times the temperature in Kelvin of 328.15, all over the pressure, which was 1.166 atmospheres, times the volume of 0.225 liters, will give me the molar mass of the gas. Completing this, you get a gas molar mass of 31.93 grams per mole, which I would guess is probably oxygen, because oxygen is 32 grams per mole. Questions? The hardest part of these should be rearranging the equation. Let's look at another example. A sample of dinitrogen monoxide gas has a density of 2.85 grams per liter at 298 Kelvin. What is the pressure of the gas in atmospheres? Okay, so right off the bat, I see I have N2O. So that tells me something. That tells me the molar mass, which is going to be 44.02 grams per mole. It has a density. Density is mass over volume equal to 2.85 grams per liter at a temperature of 298 Kelvin. We have been asked to determine the pressure of the gas. Again, when you're dealing with density, molar mass, and so on and so forth, the equation that ultimately you are using is PV equals mass over molar mass times RT. So if I divide both sides through by V, I get P is equal to the mass times RT divided by the molar mass times V. Now, M over V is equal to density. So this comes down to the density times RT over the molar mass is equal to the pressure. So plugging this in, pressure is equal to the density, which is 2.85 grams per liter, times R, which is 0.0821 atmosphere liters per mole Kelvin, times the temperature in Kelvin, which was 298 Kelvin, all divided by the molar mass of the gas, which was 44.02 grams per mole. And that will give us the pressure of the gas, which comes out to be 1.58 atmospheres. Questions? You'll notice I'm pretty much using a very small set of equations and then just being able to manipulate those equations. One of the equations I'm using is the ideal gas law, PV equals nRT. One of the equations I used was Dalton's law of partial pressure. Now today, one of the equations I've been using is PV equals mass over molar mass times RT. And then just manipulating those three, that really all I've done is manipulate those three sets of equations to solve for various variables that I need to solve for. Let's look at another example. A sample of gas has a mass equal to 38.8 milligrams, or in other words, 0.0388 grams. Its volume is 224 milliliters, or in other words, 0.224 liters, at a temperature of 55 degrees Celsius. 55 degrees Celsius is again 328.15, and a pressure of 886 torr, and we convert torr into atmospheres by dividing by 760. Make things work, which is 1.166 atmospheres. Find the molar mass of the gas. Again, I'm going to start with PV equals mass times RT over the molar mass. Just another way to write that same equation that I've been working with. This is just an easier manipulation. Multiply both sides through by the molar mass, and you get PV times the molar mass is equal to MRT. Divide both sides through by PV, and you get the molar mass is equal to MRT over PV. So using that information, the molar mass is going to be equal to the mass, 0.0388 grams, times R, which is 0.0821 atmosphere liters per mole Kelvin, times the temperature in Kelvin of 328.15, all divided by the pressure in atmospheres of 1.166 atmospheres, times the volume, which was 0.224 liters. And you get a value for the molar mass of 4 grams per mole, which tells me that this is probably helium. No, I'm not expecting you to know what the gas is based off of the molar mass, unless I give you a list of gases, and then I would expect you to be able to pick it out of the list of gases that I give you. But I'm not expecting you to know helium's 4, oxygen, it's, you know, I got 32, so it has to be oxygen. Oh, I got 2, so it has to be hydrogen. I'm not expecting you to automatically know those things. I'm expecting you, though, if I give you a list of gases, for you to be able to pick out what the gas is. Questions? Yes. The atmosphere torr, 1 atmosphere is equal to 760 torr. Other questions? And again, you will be given your pressure conversion factors. And technically, you've been given the temperature conversion factor. I don't give you the conversion factors for volume, because if you can't do milliliters to liters by now, that's a pretty sad state. So here is an example of where I said, oh, I wouldn't expect you to be able to tell me what the gas is unless I give you a list of gases. So here we have a mass equal to 1.325 grams of an unknown compound that has a volume of 368 milliliters at a temperature of 114 degrees Celsius and a pressure of 946 millimeters of mercury. We have been asked to determine the identity of the gas. Anytime you're asked to determine the identity of the gas, it's asking you to determine the molar mass of the gas. So this tells me I'm going to be using PV equals MRT over the molar mass, multiplying both sides through by the molar mass. You get PV times the molar mass is equal to the mass times RT. Dividing both sides through by PV, you get that the molar mass is equal to the mass times RT over PV. We have R involved, folks, and anytime we have R involved, that is dictating what the units must be. Our unit of volume must be in liters, so we need to convert this milliliters into liters. Our temperature, the only acceptable unit for temperature is that of Kelvin, so we need to add 273.15 to it to get 387.15 Kelvin. And our unit of pressure has to be in atmospheres. So we're going to divide by 760 to get 1.245 atmospheres. Now, using our equation, molar mass is equal to the mass, 1.325 grams, times R, 0.0821 atmosphere liters per mole Kelvin, times temperature of 387.15 Kelvin, all divided by the pressure, 1.245 atmospheres, times the volume of 0.368 liters. And you get a value of 91.9 grams per mole. Now, we got to figure out who this belongs to. So I gave you NO2. Well, NO2 means it's 14 plus 32. So we're talking 46 grams per mole. N408, 4 times 14 plus 8 means it's 64 grams per mole. N306, 3 times, oops, that is incorrect on N408, let's redo that. That is 184 grams per mole. N306 is 138 grams per mole. N204 is 92 grams per mole, which is what we came out with. So our compound would be N204. Now on the test, I actually would give you both the formula and the molar mass, so you didn't have to calculate all the molar masses. But here you had to do both. Questions? So, one more question. What is the molarity of a gas at STP? So PV equals nRT. We know that molarity is N over V. So rearranging this equation, P over RT equals N over V, which would be equal to our molarity. So our pressure is 1 atmosphere. Our temperature is equal to 273.15 Kelvin. And R is equal to 0.0821 atmosphere liters per mole Kelvin. We need N over V, which is the molarity. So plugging this information in, we have 1 atmosphere divided by 0.0821 atmosphere liters per mole Kelvin times the temperature in Kelvin of 273.15 Kelvin. And that will equal the molarity. The molarity, therefore, is 0.0446 molar for this gas. Questions? Again, probably what should be the hardest thing is manipulating equations to solve for the desired variable. But everything boils down to 3 key equations that we have discussed since Monday. The ideal gas law, Dalton's law of partial pressure, and then the third is the pressure times volume is equal to the mass times RT over the molar mass. Everything boils down to those 3. It is a matter of manipulating those 3 to solve for the desired variable. And that, folks, ends new material.